Okay, in the linear mode, the growth of the silicon dioxide will be linear with time, and the reaction in this stage will be limited by a number of silicon atoms available to react with the oxidants. Either it's dry ox or wet ox. Okay, so water vapor or oxygen gas. Okay, so the reaction will be limited by number of silicon atoms, and we discussed a little bit about the effect of using 100 wafers against 111 wafers, right? That in terms of the density of silicon atoms available for their reaction. Okay, so the growth rate begins to slow down as the thickness of the silicon dioxide grows thicker and thicker. So then it's going to enter into a parabolic stage where the reaction will slow down a little bit. It's no longer linear, but it's going to be slow down in terms of the rate and the gradient. So it typically begins around 500 angstrom above, or about 1000 angstrom of oxide thickness when it's already grown. And in this stage, the silicon atoms are no longer exposed to the oxidant. Instead, for the oxidation process to continue, the oxidants need to diffuse through the existing silicon dioxide thickness in order to get to the silicon to continue the growth process. Okay, so in this condition, the reaction will be limited by the diffusion rate of the oxidant through the silicon dioxide. Okay, remember the barrier we discussed last week? Through the barrier, which is silicon dioxide, the existing one on the surface, to be able to get to the silicon atoms on the other side. So that slows down the reaction. And we will use Dill growth model as a way to describe, as a mathematical way to describe the growth of oxide on the surface of our silicon in this case, right? So it's going to be used to predict and interpret thermal oxidation of silicon in device fabrication. So we have also discussed this before we stop in the last class. So we've discussed all the three fluxes, F1, F2, F3. You can see the interfaces there. Okay, Cg is the concentration of the oxidant in the gas form. Cs is the concentration of the oxidant in the solid form once the oxide is grown. C0 is the peak concentration on the surface, and Ci is the concentration at the silicon dioxide and silicon interface at the rear side, if you like. Okay, and the oxidant is coming from the left. Okay, the flux is coming from the left. So the moment you've got your silicon dioxide ready or already grown, so the oxidants need to diffuse through the oxide to be able to get to the silicon down here. Okay, silicon wafer is down here. Right, so F1 is for the gas transport flux, which is the oxidant in the process. F2 is the diffusion of flux through the silicon dioxide in the existing layer, and F3 is the reaction flux at the interface of silicon dioxide and silicon in order to continue the growth process. So these three fluxes can be described in the form of three different equations. Okay, F1 equals to Hg. Hg is the mass transfer coefficient times Cg minus Cs, right? Cg minus Cs is Cg minus this. So that's pretty much the difference between the flux, right? Between the incoming flux and the one that reaches the surface of the oxide times the mass transfer coefficient. And then F2, let's go back to F2, which is the diffusion flux through silicon dioxide. So that will be given by negative diffusivity times ddx of C, concentration of C. So that is also equal to D times C naught minus C1. Let's have a look at C naught minus C1. So that's here, C naught minus C1, the difference between this over the thickness of the oxide. Okay, sorry, the thickness of the oxide, X ox. Let me just approach a friend joining here. Okay, so C naught minus Ci over X ox. So C naught minus Ci over X ox. Okay, the thickness of the existing oxide. So that will give you your C2 or F2, sorry, and F3 eventually is the reaction coefficient at the surface of silicon, and that will be given by Ks times C1, and Ks is surface reaction rate constant times C1. C1 is the flux or the concentration available at the surface. Okay, so F3, reaction flux at the interface. So it may not be obvious yet as to how can you use these equations, but eventually I'm going to give you maybe today or tomorrow, I'm going to give you one example for you to try out to calculate the oxidation process, the thickness of the thermal oxidation using Dilgrove model. Okay, and you can try out and see. C naught is equal to H times PS. C naught is given just now, right? C naught is what you have on the as the concentration at the peak, at the surface, at the peak, at the surface of the silicon dioxide, equals to H times PS. H is the Henry's constant. Okay, this is called Henry's law. So H therefore is Henry's constant. Then PS is partial pressure of the oxidant at the surface. Okay, partial pressure at the surface of the silicon dioxide. Okay, take about the interface. So first, before you do this calculation, if you get a question on this, first thing to do is to sketch this. Okay, sketch this interface. Then write down your F1, F2, F3, CG, CS, C naught, CI. X ox, right? Label all the regions, okay? The incoming flux, the SiO2 layer, and the silicon onwards, right? Label that first, and then write down your F1, F2, F3 equations. Then only look at the parameters given in the equation, right? So these are all derivation. At steady state, F1 is equal to F2 and equal to F3. So all the three fluxes are equal at steady state. So in this more derivation, you can go through later on. So we need to know how do we convert the flux. Okay, so we have the flux F1, F2, F3. So then the interest is how do we then convert the flux into oxide thickness growth rate, and eventually to know the final thickness grown in a specific process, either it's in linear mode or parabolic mode, right? So that is the main interest of this model. Okay, kita akan guna the figures given later on to plug into either one of the steps, linear or parabolic, and then try to get your oxide thickness. Okay, so you can also see this as this. Okay, silicon dioxide is what you want to grow. So the thickness of the oxide, your flux coming from the top or from the front, if you like. This is your silicon wafer, and you want to grow your oxide on top. Okay, so flux is equal to N1 times ddt of X ox, your thickness of the oxide. Your N1 is oxidant molecules per unit volume required in order to form a unit volume of SiO2. So how do we translate the oxidant volume, the oxidant molecules, to SiO2 volume? We want to change this to this. So don't worry about the derivation, and you can go through later on. So if you talk about N1, for example, oxidant molecules that we want to convert into unit volume of silicon dioxide, it's going to be different if you use dry ox and or wet ox. Okay, so if you talk about dry ox, for example, dry is here and then the wet is here. You can look at the difference here in terms of the value of N1. Okay, N1, you can go back to the previous page. The oxidant molecules per unit volume required in order to form a unit volume of SL2. Okay, oxidant to SL2. So look at the difference there. For dry ox, your N1 equals to 2.3 times 10 to the 22 per cm cube. Okay, that will form silicon dioxide. And for wet ox, the N1 value is 4.6 times 10 to the 22 per cm cube to form silicon dioxide as well. So from here, you can already tell that the value is higher for wet ox. So that's one of the reasons you will end up with thicker oxide converted from unit volume of unit molecules in the oxidant okay. So Xox can be written as this equation, the one above. So for the case where your T is large, case one where T is large, so if you relate that into the previous parabolic mode, for example, a linear and parabolic mode, you can always come back to here, sketch this. Sketch this X ox on your y-axis and T on your x-axis. Okay. So when you talk about large T, so that means you're talking about the one on the right, isn't it? Large T is here. Kalau kita boleh bahagi dua, for example, then large T will be on the right, of course, further to the right, and small T will be to the left. Okay, small T kat sini lah baru start, start process. So X ox for large T can be approximated as to be equal to square root BT. Okay, square root BT. We're going to have a look at that later on. And for small t, square root BT. For small t, okay, B over AT. So you can relate that to the linear mode and parabolic mode. Okay. So sama juga ini, if you want to see the relationship between your X ox on the y-axis to T, then you can say that your X ox is approximately proportional to T in the linear mode. Okay, and when it enters the parabolic mode, parabolic lah, so it's going to be the X ox will be proportional to square root of T. Okay, the dependency. So oxide growth rate slows down with increased oxide thickness. So we talk about the reaction limiter just now, where in the second phase, the reaction will be limited by the silicon dioxide thickness available, and therefore that will affect the diffusivity of the oxidants through the oxide. And this doesn't exist in the linear mode. Okay. So ini sama. So you can see that for A, where you just started the process, the reaction interface reaction is the limiting step, where this is controlled by number of silicon atoms. Okay, at the interface reaction due to number of silicon atoms. And in the second phase, the reaction is limited by the transport or the diffusivity in this case through the oxide. Okay, so somewhere, yeah. So we can always relate this to the same curve. Okay. Okay, now I'm going to give you some example electron. You can try and calculate. So let's see the effect of temperature on the rate constant. So we call this B and B over A as rate constant. Okay, B is now B and B over A tadi. Okay, B here and B over A as the rate constant. So let's see the effects on the rate constants. So the one on the left, the graph on the left is parabolic rate constant B, and the one on the right is linear rate constant B over A. So the effect on B and B over A. So the x-axis shows the temperature, but it's inverted. So increasing temperature means going to the right, to the left in this case. So our axis there is 1000 over T. Yeah? So if you increase the temperature, you're going to end up with lower 1000 over T, right? 1000 over T is lower, means going to the left. Higher T. Higher T. Okay. Somewhere, yeah? So if you look at the constant on for parabolic on the left and linear on the right, you can see that firstly the slope is negative. So negative slope here means increasing temperature, which means going to the right, going to the left. So we'll increase the parabolic rate constant and linear rate constant as well. Okay, dua-dua sama. Dapat negative gradient, and higher temperature means going to the left, going towards the origin. Okay, so you can also see here the parabolic rate and linear rate. You can see the difference between wet ox and dry ox. Okay, for parabolic rate, for example, you can see that the magnitude of the difference between wet and dry. So dry di bawah, wet ke atas. So that's the difference between the rate constant. Okay, sama juga with the one on the right. For the linear rate, dekat linear region when we just started. So the difference is here as well. You can see wet ox is up there and dry ox is down here. You can also see the difference between 111 wafer and 100 wafer. Okay, you can see the gradient for 111 is always higher than 100. 111 up there, 100 down here. Okay, for wet ox. So the same goes to dry ox as well. So 111 is up here, 100 is down here. Okay, so the difference is like, say if you take, if we look at the right graph, a linear rate constant, let's just pick 0.8, for example, 0.8. Okay, so that means, okay, about 1000 degrees C. So if you look at the difference between 100 and 111 for dry process, dry bawah, look at the difference there. Okay, if you look at the difference on the y-axis, so that's probably dia ni a log scale. So log scale on the y, so that's probably 009 versus 007, something like that, right? Perhaps 002 difference, 0.02 difference between 111 and 100 for dry ox process in linear region. Okay, so you can see for yourself later on the difference between B, which is the parabolic constant, the left, and B over A linear. So the constant is already different. Okay, so when you use your calculation, when you use this constant in the calculation later on, you have to pick the right values for the right parameter, B or B over A in dry ox environment or wet ox environment. Is it on 111 or is it on 100? So you have to come back to the temperature as well. So if you run your oxidation process, say 900 degrees, then of course it's going to be different if you compare to 1000 degrees C. Okay, your B and B over A will be entirely different. So you can ambil B and B over A daripada sini, daripada graph ni. Come back to this, check the temperature, is it dry or is it wet, is it 111, is it 100? then check what's the right value for you to use. Okay. So ini pun sama juga, wet versus dry, just in the form of table. Okay, wet versus dry, and then you can also see the difference between 100 and 111. Okay. So let's have a look at diffusivity of materials in silicon. Right? So let's have a look at diffusivity. So in this case, have a look at H2O. Okay, O2 versus H2O. Diffusivity. Don't have any. Okay, right. Okay, that's the difference between these two. So if you still have to look at the temperature or temperature, and then you can invert that as 1000 over T as well. Right, oxide on wafer topography. If you're growing your silicon dioxide on a planar silicon, so the one that you have here top, so you will get a very uniform or smooth layer of silicon dioxide on the silicon. So bukannya you grow on the front, you are growing on the side as well and at the back. If you expose the whole silicon wafer in the first side, it's at the back as well. So it is because you have silicon atoms everywhere, isn't it? So you have on the top, the back, and on the side as well. Ini just nak tunjuk illustration ya, nak simplify so that you can see if it's on the front surface and how does it look like. Okay, so but actually you're gonna get your whole silicon exposed, and therefore you're gonna get your oxide on other areas as well. So on the other hand, if you have uneven silicon surface, so case 1 ialah case even ke atas. So what if you have uneven? For example, you have something on silicon. You have silicon, but it's not even. So the way the oxide grows is it's going to follow your underlying topography. Jadi lebih kurang macam ni kan? So that means the growth rate is similar at all locations on the silicon wafer. So that's why you end up with something like that. It will just follow the topography of the underlying silicon, right? So before that, before you get this kind of structure, you can actually buat lithography dulu lah, lithography and etching, but this one I don't cover yet. So before you come to this kind of structure, yang ada trench ni, this one we call it trench. Macam longkang ni. In fact, you're going to call it trench. So to be able to get this kind of trench structure, you need to do patterning first. But you don't have to worry about that yet because patterning will be our next topic. Patterning. You're going to pattern kan dia. So that means usually you grow silicon, you akan dapat the whole blanket, the whole surface is silicon, right? But if you in the actual fabrication, we may use certain areas with oxide and some other areas without oxide. So that means the oxide needs to be patterned first. And you may have oxide here as well, say here, and then you don't have, and then you have another oxide coming on the sides. And this can only be done by lithography process. Sebab bila you run oxidation, you akan dapat blanket je. Semua ada. Tapi kalau you nak define area mana yang you nak buka dan area mana yang nak tutup, area mana you nak buka dan area mana you nak tutup, then you have to do patterning, right? Patterning, and this patterning is done by lithography process. Litho process. Okay. Nanti kita akan belajar lepas ni. Next topic, how do you, from the blanket oxide that we have now, the blanket oxide. Okay, the blanket, let me just write it, blanket. Blanket means you cover all. Macam selimut, blanket selimut, cover semua. So, yeah, that's how the oxide is grown. But then for the actual fabrication, you need to open certain areas, and that can only be done by lithography. Okay, that can only be done by lithography. So you need to do that, right? So opening here means you buka kat sini lah. Mula-mula tadi kita ada silicon kan, silicon oxide tengah ni kan. Sekarang kita nak remove this portion, and tinggal kiri kanannya, right? So this is called patterning process. So lepas you dah pattern, we're gonna cover this one more later on dalam litho and etch. Bila you dah remove this, saya tunjuk sikit lah briefly before we learn the details later on. Once you remove, you can actually remove silicon at the exposed region. You can, bila you dah remove the silicon dioxide kat tengah, dia dah kosong, you can then etch. Etch to remove, removal. Etch is removal. Kita akan cover later on. Etch means remove. So you can actually remove this silicon in the trench. So that's why you end up dapat silicon macam ni. So it was due to oxide that was patterned, and then silicon was then etched, and you dapat trench ni. Trench ni just siliconnya. Then lepas you dah etch silicon tu, you can then remove this silicon dioxide as well, and then this oxide kat sini, dan kat sini dah tak ada lah. You will be left with pattern silicon only. Okay. Then kalau you nak grow oxide again, you can grow oxide again on this pattern. You can dapat oxide tu dia akan follow this. Okay. Can you follow now? Do you get what I mean? Sebab dia ulang-ulang banyak kali sikit kan. Dia fab dia akan jadi macam ni nanti eventually. Sekarang kita baru belajar satu proses. But eventually it's gonna be like oxide, then patterning, then etch, then you oxide again. Dia akan come back here. Apa ni? Every now and then dia akan masuk dalam proses. So it will be part of the process flow. So okay for now. Kau nanti you dah pening. Sebab kita belum belajar lithography and etching. But just to show that if you grow oxide on trench, so the oxide is going to take the morphology of the underlying silicon, because the growth rate is similar at all locations. Maknanya oxide dekat semua tempat dia akan grow at the same rate, so that's why dia akan follow lah. Kalau you punya trench, you have your trench like this, tiba-tiba you grow oxide, your oxide blanket, tapi dia tak follow underlying topology. You dapat straight, contoh. You dapat straight line. What does it mean? You dapat oxide macam ni. So, you dapat kat sini, sini thin sikit. Sini tengah thick. Dan kat kanan thin balik. What does it mean? Anyone? Kalau you ada trench kat bawah, ada longkang. You ada longkang, you ada trench kat bawah. Tiba-tiba then you grow oxide. It's supposed to be following the morphology of the underlying silicon. Maknanya dia kalau trench, oxide tu pun dia akan grow macam trench juga lah. Dia akan macam jadi coating. Kalau you cat dia akan masuk dalam lubang sikit, naik balik kan. Kalau you buat cross section lah. Tapi tiba-tiba bila you grow oxide, then suddenly the top apa silicon dioxide is flat. So it doesn't follow the underlying layer of silicon. So what does it mean? Apa maksudnya? In terms of the growth rate of your oxide. Anyone? Any idea? Adakah dia punya growth rate dia uniform across the surface? If you get a very flat silicon dioxide, Is it uniform across the surface? Tak uniform kan? Growth rate tak uniform, right? So growth rate dia tak uniform lah sebab it's not supposed to be flat. Kalau dia uniform, dia akan follow exactly, dia akan copy the underlying layer. Silicon dah ada trench, but kalau kita grow oxide with even rate everywhere, even growth rate everywhere, dia akan follow exactly the underlying layer. Dia, well, not exactly lah. Dia akan ada rounded sikit. Kalau kat bawah tu ada tajam, silicon tu tajam macam you buat square shape punya longkang lah. So the growth rate will not be like tajam juga dah masuk dalam. It will be a bit rounded. Sebab dia ada smoothening effect dekat trench tu. Dia follow trench tapi dia tak adalah macam tu kan sebab dia bukan the exact process. Dia growth. Dia akan ada some apa diagonal component of the growth rate if you like, right? So dia akan rounded tapi dia akan masuk jadi trench juga, right? Dia akan follow the underlying topology. So that is the case when you have a uniform growth rate. So tiba-tiba kali ni kita dapat flat lah. Flat means something is wrong somewhere and it's not uniform because nampak kalau if it's flat then that means the central part, the trench part tu, dia punya growth rate is higher, isn't it? The growth rate is higher in the trench part if you compare to the sides, to the left and to the right, because your oxide thickness in the central part is thicker, but your oxide thickness on the sides, left and right, are thinner. So maksudnya the growth rate is not uniform throughout the surface. So yeah, so that's the thing. So jawapan dia tak uniform lah. So that's what I want you to understand from this slide. Okay, don't worry about the patterning yet. Don't worry about the etching of silicon after patterning because that's going to be covered in lithography and etching respectively. Right, if you perform a TEM, transmission electron microscope, that I discussed in wafer characterization before we started off with clean room. So we talk about TEM. So TEM can actually tell the crystalline structure of your layer, okay, of your material. For example, in this case, kita grow kita punya silicon dioxide on crystalline silicon, okay? So if you draw a schematic, so it's going to be something like that. Silicon and silicon dioxide is grown from silicon, okay, consuming silicon. And silicon is, say, 100. 100 is monocrystalline or polycrystalline? 100? Anyone? If your wafer is 100, is it monocrystalline or polycrystalline? Mono, huh? Kenapa mono, Haziq? If it's 100, why is it mono? You boleh unmute. You can write as well. Anyone else as well? Kalau nak tu tulis je, it's okay. So apa dia mono? If the wafer is 100, so you say it's mono. Why is it mono? Sebab dia ada satu crystalline orientation saja kan? It's just 100. There's no 111, there's no 101, there's no something else. It's just 100 throughout the lattice. Bila kita potong ingot tu dah grow 100 dah. There's no other orientations inside the ingot. And when you cut the wafers, and it's just 100 because it's just part of the ingot, isn't it? So it's just one orientation, therefore it's mono. So bila you tengok growth of oxide on silicon here, TM, what do you see in the below, in the lower part of the TM? Can you see any crystalline atomic periodic arrangement of atoms? Can you? In the lower part of the TM image. Bawah, nampak tak? Do you see any particular crystalline arrangement of atoms? Nampak dia punya arrangement tu periodic or there is no period at all? It's just messy. Kan? Nampak kan dia punya crystalline arrangement is very, very periodic, right? Very well arranged because it's 100. Dia satu crystalline orientation je. Okay, so that is the silicon that we have grown from the ingot and cut into wafers. So satu crystalline orientation, very periodic. You can relate this to what you learned in 386, monocrystalline, infinite periodicity, infinite periodic arrangement of atoms. Sama semua tempat. Tak ada nampak satu distortion pun anywhere in the lattice. Then you grow the oxide on top. Okay, tengok sekarang, the upper part, you have the oxide. Silicon oxide. Do you see any crystalline arrangement of the oxide on the silicon in this case? No, right? Okay, kenapa dia no? Why don't you see any sort of arrangement at all? Tak ada langsung pattern. Kau dah nampak satu cluster, then lost. Satu cluster, then lost. Kenapa tak nampak langsung? Kenapa there is no crystalline arrangement at all? Just relate back to what you've learned before. Kerana ia apa? Dia punya, what is the crystallinity of the oxide? This oxide? Jawapan dah tu kat atas tu. Kenapa tak ada? Why don't we see any arrangement at all? Sebab apa? Anyone? Right, kan? Sebab dia amorphous lah, kan? Sebab dia amorphous lah, tak ada arrangement at all. Nampak dia serabut je. What if you see some cluster of crystalline arrangement and then gone, tak ada, tepi tak ada. Tiba-tiba nampak lagi. Tiba-tiba gone, tak ada. Tiba-tiba nampak lagi. So what does it mean? What is the crystallinity of that particular layer then? Satu tempat ada crystalline arrangement, then tepi tak ada, then tepi sana ada pula, then tak ada pula. Poly, right? Okay, that's polycrystalline. Okay, sebab dia ada cluster, dia poly, dia ada mono dalam region yang small region, ada mono, dalam tu mono semua. Satu region mono, then mungkin sebelah tu hilang sekejap, ada amorphous in between perhaps. And then you ada, kalau amorphous terlalu banyak, then we call that as microcrystal. Remember microcrystal? Soalan, I think I'm not sure about whether it was the test question or assignment. I think assignment question kot, 386 dulu. Kalau you ada mixture of amorphous plus crystalline, then we call it as microcrystalline. Then you have to look at the crystalline volume fraction, XC. Okay. Tapi kalau you nampak mono, then tiba-tiba ubah arah, another mono, then we call that as poly, because dalam satu region is mono, but then the neighboring region is no longer of the same crystalline orientation. Okay. So that's what you see from TF, very clear. So in this case, it's amorphous silicon dioxide grown on monocrystalline silicon wafer. Okay. So look at the interface here. Let's zoom at the interface. Kita tengok ke interface ni ya. Tak tengok tempat lain. What do you see at the interface in particular? Anyone? What do we see exactly at the interface? Transition, right? Kita nampak ada transition from mono to amorphous, right? So mono kita dah habis crystalline. Okay, dia punya monocrystallinity itu dah habis. Lattice is terminated already. Then you start seeing amorphous. This is possible if you're talking about interface. Then in your semiconductor devices, depending on materials and devices, you probably have transition from mono to amorphous. In some cases, mono to poly. In some cases, mono to another mono. Possible juga. So this is only one example of the many more possible examples. Okay. So my point is, you can actually look at zoom into the interface and see. In this case, you'll see mono to amorphous. But in some other cases, you'll probably encounter mono to poly, amorphous to mono, amorphous to poly, amorphous to amorphous, poly to poly. Tengoklah you punya interface tu is made of what material for what devices. Okay, so it's possible. So that's the point. Sekarang at least you dah nampak. You tengok TM, you can tell already. Below is monocrystallinity, atas amorphous. Okay, very clear cut. Okay, the same thing from the TM is translated into this schematic. So you nampak the below part is monocrystalline, regular, periodic, infinite arrangement, and then dekat atas ni silicon dioxide, there's no particular arrangement at all. There's no periodicity at all. There's no repeating patterns at all. So therefore, it's amorphous. Okay, so amorphous on monocrystalline, right? So there are a few factors affecting the oxidation process. So ada beberapa. I'm just going to go through perhaps 1 or 2 pages, see how many more do I have. Quite a number. So I'm just going to cover perhaps another 2-3 pages. So there are a few factors affecting the thermal oxidation process. Okay, temperature. So we've seen just now on the graph of linear rate and parabolic rate, parabolic constant and linear constant tadi. So we've already seen the proof that temperature affects the oxidation. Okay, so if you see your B and B over A is different, then of course that's going to affect the oxidation already. Temperature is going to change. Ambient type, either it's a dry ox or wet ox, or either you add on HCl to the system. So that's going to affect the oxidation process as well. So if you run your process at different pressures, for example, so that's going to change the oxidation rate, substrate doping of your wafer. Okay, kalau you run one wafer with 10 to the 14 per cm cube in terms of its doping level, for example, then another wafer at 10 to the 19, then you're going to see some difference in terms of the oxidation rate. And also substrate crystallography orientations. We've seen this now in our linear rate and parabolic rate constant graphs. So you've seen the difference. Tadi yang negative slope tu. So you've seen the difference between 101 versus 100. Okay. So let's look at the dopant, high doping concentration effect. So dopants increase oxide growth rate. So during linear stage of oxidation, N-type dopants increase growth rate. Dopants cause differential oxidation. So dopant affects the growth rate, and how it causes differential oxidation. This is the mechanism, differential oxidation. Of how does it affect the oxidation? So it's called differential oxidation. So results in formation of steps. Dia ada step. You akan dapat some steps. Bila you nampak step, then you're going to see some difference in the thickness. It affects etching process as well later on. Bila kita belajar oxidation now, so it looks like it's just an oxidation process. Tapi bila kita eventually when we talk about the whole process flow dalam fabrication, then you're going to see oxidation, litho, etch, and then you might redo the oxide, and then you might litho and etch. Some cases you do oxide and then you do the lithography, and then you might do a double lithography as well. We call that a double patterning process. You buat satu litho and then habis tu, you litho second time, then you continue. So there's also that case. Okay, so sekarang kita hanya akan belajar independent process on its own, but eventually when I talk about the whole fabrication processes, or we call it as process integration, we're going to cover this at the very end of the course. Yang mana kita akan tengok macam mana kita combine multiple processes in certain flow in order to fabricate certain devices. Okay, so we call that as process integration. So it involves integrating processes in different ways in order to achieve something or fabricate some structures. So tapi sekarang kita akan belajar independent process on its own. Tapi the real case is never that process alone. It's always this plus this. You repeat this and then you come back to this. Dia akan jadi ni, dia akan jadi berulang-ulang. So that will be captured in process flow. So okay, effect of high doping concentration, for example, dry oxidation at 900 degrees C as a function of phosphorus concentration. So this is the concentration of phosphorus. So we are looking at 1017 up to 10 to 21. So you can see the difference in terms of the B over A and B, like the linear rate and the growth rate. So you can tell that by the micron per minute and micron square per minute. So you can see if you increase doping level, at some point, you're going to see a gradual increase in the rate, by the way. Cumanya bila awal-awal tu in the region of 17, 18, the increase is not that obvious. But if you go beyond 1019, for example, if you go beyond 1019, you start to see the gradient starts to be developing. Mula-mula nampak macam fairly flat, but it's not flat, it's not zero, it's not a gradient zero, tapi dia ada slightly positive, tapi you start seeing a more significant gradient after 1019, and then after 1020 you can see that, right? Okay, so what do you get? So if you start off with for example, kalau you ada silicon wafer, ini all silicon wafer. So this silicon wafer has a say the n level n doping is 1014 contoh centimeter minus 3, and then you introduce n plus perhaps 1017 or 18 lah, so let's say 18 lah, 18. So you have a very localized 1018 dope on 1014 wafers. Kita akan belajar this in diffusion later on, or the details. You don't worry about that yet. Sebab sekarang ni, this means kita start dengan 1014 punya wafer, doping level, untuk awal-awal tu. Yang kita dah dope waktu Czochralski sebelum ni, 1014 only. And then along the process, you diffuse another layer in selective region. You diffuse 1018, only this region. Okay, only the region you dope 1018. Okay, how did you do that before we discuss the effect on oxidation? Can you imagine how do you use oxide to introduce this selective doping of 1018? Do you get any idea? Macam mana nak dapat 1018 doping tu? Kita dah discuss very briefly before this. Anyone? How do you use oxide in this case to fabricate or to diffuse this 1018 small region on the 1014 wafer? Any idea? It's okay, it may not be obvious yet. Remember, we talk about the SiO2 as mass. Kan, kita belajar kan, last class kan? SiO2 boleh jadi mass kan? You want to block the doping in certain region and you want to let the doping goes into the silicon in certain region. So in this case, you nak dapat 1018 ni, you just have to open this, you remove SiO2 kat tengah ni, then you masukkan dopant, say phosphorus in this case, but N+, you diffuse kat tengah je, and then lepas you dah habis, you remove this oxide. Pakai HF boleh remove oxide kan, silicon oxide. You remove this, then you're going to end up with the original structure. 1018 on 1014. Okay, so sekarang dah nampak sikit kegunaan oxide for this particular case. But the point on this slide is not that. Cuma saya nak relate balik je. The point on this slide is, if you use 1018 selective region on 1014 original wafer, you run oxidation, dry oxidation, 900 degrees C, you're going to get this sort of oxide. Dia akan higher growth rate dekat tengah and lower growth rate dekat tepi. Why? Because N plus is here, and N plus increases the growth rate. Okay, increases the growth rate. So you punya micron per minute in the central part is higher if compared to the sides. Okay, so katalah dia double lah, for example. So this katalah kat tengah ni growth rate double, 2x of kat tepi ni katalah x ya, kat tengah 2x. So you're gonna end up like that. You dapat macam ni, dan dia akan kembung kat tengah sebab the presence of N plus, which has caused differential oxidation. Sebabnya kat tengah ni dia akan ada differential oxidation, and that means higher growth rate lah. Dekat certain region higher growth rate, dekat certain region lower growth rate. So differential oxidation here, in the sense that it causes the growth rate to be double in the central part and just X on the sides. So then you can dapat that kind of structure dekat tengah. So I'm just gonna stop here, and then I'm gonna continue tomorrow on the rest of the factors that can affect the oxidation process. Okay, is it okay so far? Is it clear? All good? Okay then, kalau clear then I'll just, okay, so far clear, right? Good. So I'll see you tomorrow 11 to 12, right? Tuesday? Okay, jumpa esok, bye-bye. Take care, assalamualaikum.